Hello, everyone. Thanks for making the time to come to this session. My name is Vamshi Khandala. I am the Chief Strategy Officer for Granite River Labs. We are an end-to-end test solutions vendor based in Silicon Valley with multiple locations worldwide. I am supported here in this session today by my colleague, Miki Takahashi, who is our EVP of Engineering. Today, we are representing the PCIe SIG, and we'll be talking about the PCIe 6.0 specification and how it advances artificial intelligence and machine learning applications. A quick snapshot of PCIe SIG. This is an organization that defines the PCI Express I/O bus specifications and related form factors. It currently has 900 member companies worldwide, and this is the highest number of member companies in the last 12 years. It creates specifications and mechanisms to support compliance and interoperability. The board of directors for 2021-22 reads as the who's who of the industry: AMD, ARM, Dell, IBM, Intel, Keysight, NVIDIA, Qualcomm, and Synopsys. Today's agenda: I will be talking about the PCIe 6.0 specification, introduction, and demand drivers. We will touch on markets as well as use cases. We'll also talk about some features. We will discuss PCIe technology progression from PCIe 1.0 through 6.0. We'll talk about design considerations with PCIe 6.0 technology. We'll have a use case as an example, and then we'll summarize what we spoke about. PCIe 6.0 specification, introduction, and demand drivers. PCIe 6.0 specification is the future of PCIe technology. PCIe specification, as is well known, doubles the I/O bandwidth every 3 years and continues to meet industry demand and remains ahead of the increasing demand for a high bandwidth, low latency interconnect for compute intensive systems. As you see in the graph on the right-hand side, from PCIe 2.0 all the way to PCIe 6.0, the data rate has been doubling every 3 years. PCIe 5.0, which was released in 2019, was supporting 32 gigabits per second. PCIe 6.0, which is released this year, is supporting 64 gigabits per second, which is 256 gigaflops, gigatransfers per second in a by 16 configuration. Moving forward, we will then take a look at what it means to the industry. From a PCIe 6.0 technology benefits as well as adoption across various markets viewpoint, some of the technology benefits for PCIe 6.0 are double bandwidth. I think I mentioned this before. It increases the data rate to 64 gigatransfers per second, which is double the PCIe 5.0 specification, which is a data rate with maximum bidirectional bandwidth of up to 256 gigabits per second for a by 16 lane configuration. It also supports low latency by utilizing flow control units with fixed sizes, which is Flit, that enables lightweight forward error correction with PAM4 signaling and cyclic redundancy check, CRC, with no latency impact. It's also backwards compatible. PCIe 6 is backwards compatible through the generations 5, 4, 3, 2, and 1. It also supports a low power state that allows traffic to run on a reduced number of lanes to save power, which is a critical feature. And it maintains at least one active lane at all times to allow uninterrupted traffic flow. Some of the key markets that PCIe 6.0 has a major role to play in is high performance computing, data centers, artificial intelligence, AI, and machine learning applications, which we will talk about more in depth today, automotive, Internet of Things, as well as military and aerospace. Why is PCIe 6.0 technology for data-centric applications important? As has been reported, as most people in the industry know, the rapid adoption of sophisticated AI and ML applications, along with cloud-based workloads, has significantly increased network traffic. This insatiable demand for more bandwidth to support these applications and workloads has accelerated the adoption of higher speed networking protocols that double in speed approximately every 3 years. And that's exactly what the PCIe SIG has been doing over the last 15 to 20 years. PCIe 6.0 specification, the latest PCIe standard, allows companies to reach these new levels of performance for their data-intensive workloads. The PCIe 6.0 architecture, as I mentioned earlier, provides 64 gigatransfers per second of high-performance bandwidth, which represents a doubling over the PCIe 5.0 technology speeds. It also enables faster and lower latency data transfers for critical real-time applications and services to perform optimally. Why is PCI technology important for data center and what it means as a data center evolves over the next few years? Right? The evolution of the data center is driven by a number of trends. Again, this is common knowledge, it's been reported. There are a few key factors here that directly play into why PCIe 6.0 is critical for data center needs to be met going forward. Right? As we know, enterprise workloads are migrating to the cloud, either it's hosted or co-located. Data centers are being architected to handle more connectivity within the data center as a basis of workload traffic changes. There's a focus on virtualization with AI ML workloads, prioritizing use of multiple processors to execute single large workloads over one computer executing multiple processes. This is a key evolution that's going to play a major role going forward. Hyperscale data centers are in a cloud setting with large computing horsepower and storage space. To support a wide set of internet applications and services, they are becoming more and more prevalent. Right? So what does this mean? The recurring theme within these trends is an explosive increase in data traffic and the need for continuously increasing bandwidth. That is where PCI technology plays a major role, and more specifically, PCIe 6.0 plays a critical path. The PCIe interface forms a backbone which moves high bandwidth data between the various nodes that includes a CPU, GPUs, etc., which then enhances the AI and ML workloads. The PCIe 6.0 architecture is a core interconnect that allows data centers to support high-speed processing and computing. PCIe 6.0 bandwidth efficiency provides the required communication speed between the network interfaces of servers and switches. And PCIe 6.0 architecture serves as a critical bridge between the CPUs and the AI accelerators. A few use cases that will go into more details as to why PCIe and the data center are so important, especially from an interconnect viewpoint. A few, let's say, useful use cases. Predictive maintenance, it's described as data collection on temperature, humidity, and load patterns. Cooling, data collection on facility customer load to trigger cooling, ramp up or down based on certain set points. Power management, that's real-time sensing data model for power usage patterns. Security, again, security as well as security applications such as automatic temperature checks, touchless authorization, payment and control systems, as well as traffic monitoring. And finally, workload management, which is tied to predictive maintenance. So these unique data center operating test cases, which are AI and ML use cases, require a lot of network traffic, which require a lot of real-time data. And PCIe 6.0, which is high data rate, plays a major role in supporting these use cases. Let's now talk a little bit about the history of PCIe specification, how it's evolved over the last few years. As I mentioned earlier, it doubles the data rate in every generation. Way back in 2003, PCIe 1.0 was 2.5 gigabits per second. PCIe 6.0 in 2022 is now at 64 gigabits per second, compared to PCIe 5.0, which in 2019 was at 32 gigabits per second. PCIe has been able to double the data rate every generation with feature implementations such as coding scheme, as well as with single modulation changes. In 2022, as mentioned earlier, the PCIe 6.0 spec employs PAM4 signaling and achieves 64 gigabits per second data rate with no increase in clock rate from Gen 5, which is a critical feature. What are the requirements that drive the evolution of PCI Express technology and some key specification features of PCIe 6.0? Some of the requirements that we are seeing across the industry are higher bandwidth driven by AI and cloud computing, higher reliability by error correction technologies, lower latency and higher efficiency, powerful equalization, that is FFE, CTLE, or DFE for hardware design flexibility, power management, and future functional evolution. This is a summary or a summation of almost all the feature requirements from the targeted application or targeted markets. And it so happens that PCIe 6.0 is able to meet almost all of these requirements going forward. And as mentioned earlier, PCIe 6.0, the spec was released this year, 2022. Some of the key features that essentially support the requirements in the markets. PCIe 6.0 supports higher efficiency error correction mechanism. That's a balanced combination of forward error correction, FEC, cyclic redundancy checks, and retry. It supports PAM4 signaling, where higher bit error rates, FBR, is greater than 10 to the power minus 6 expected. It's able to achieve low latency and high reliability with a low overhead FEC. It supports Flit mode, which is mandatory for 64 gigatransfers per second or higher data rates. And Flit mode is supported all data rates and can tolerate in higher BER. There's a new power state, L0P, that supports dynamic lane width change depending on traffic load. It supports reduced number of lanes when traffic is low and keeps the power low with minimal impact to traffic flow. And there's a new TLP format that provides room for simpler TLP parsing and supports intersegment routing, which essentially results into larger topologies. PAM4 modulation, what it means, right, compared to NRZ. NRZ, non-return to zero modulation, is 1 bit per 1 clock cycle. PAM4 is 2 bits per 1 clock cycle. You can see the difference right there. PAM4 has a worse signal to noise ratio than NRZ. However, in PAM4 modulation, higher BER is expected than 10 to the power minus 12 BER that presently exists in NRZ, which has a lot of benefits going forward. Signal equalization and the various PCIe standards. Transmitter equalization for PCIe 1.0, 2.0 is fixed de-emphasis. For PCIe 3.0, 4.0, and 5.0, it is 3-tap FFE with 11 presets. Whereas PCI 6.0 is PAM4, 3-tap FFE with 11 presets. For reference receiver CTLE, it is not applicable for PCIe 1.0, 2.0. For PCIe 3.0 and 4.0, it's first order CTLE. For PCIe 5.0, is a leg up. It's second order CTLE with 4 poles, and the gain is from -5 to -15 dB for PCIe 5.0. Now for PCI 6.0, we still maintain the second order CTLE from a reference CTLE viewpoint. It now supports 6 poles, and the gain remains the same from -5 to -15 dB. And finally, reference receiver DFE, it's not applicable for PCIe 1.0 or 2.0. PCIe 3.0, 4.0, and 5.0 support 1, 2, and 3-tap DFE respectively, but PCIe 6.0 incremental increase supports 16-tap DFE. And not only that, there are more selections in equalizer setting available in PCIe 6.0 specification. As you can see, there's a quantum jump in what PCIe 6.0 is capable of for future data-intensive applications. A specific example of PCIe 6.0 technology and a use case, in this case, we're talking about retimers. What's the difference between a retimer and a redriver? A retimer is protocol aware because it supports link EQ. A redriver is not aware because link EQ is not supported. A retimer has latency because it's protocol aware. 2 retimers are max in a system, and redriver has no latency or is pretty small. Equalization settings, CTLE, DFE, and FFE, redriver only supports CTLE. In terms of placement, retimer, there's a lot more flexibility. In terms of redriver, there's less flexibility. So as you can see, retimer supports a system which has a longer channel. Up to 2 retimers can be used between root complex and device. Now, why is this important? The next slide talks about what do PCIe architects and designers need to be careful of or need to be aware of integrating PCIe 6.0 technology. From an architecture design challenges viewpoint, in order to make sure the system is designed as it should be and the system works as expected, we are suggesting that the engineers and the architects look at 3 major factors: SI simulation, electrical validation, and functional validation. SI simulation to deal with complicated system design using equalizers, redriver, and a lossy connector channel, and to maintain a reasonably low BER regardless of PAM4 modulation. Electric validation to make sure that the signal integrity is achieved as expected, electrical performance, error rate, equalization settings, etc. Again, we're talking about 64 gigabits per second, much higher data rate. So a lot of testing will have to be done in the right way to make sure the right performance is achieved as per the data sheet or as per the product spec. And finally, functional validation to check if the performance meets expectations. Sometimes, or although I should say, FEC and CRC is implemented, if retry happens, typically performance goes down. So in repeating this important slide, From an architecture or a test integration viewpoint or design integration viewpoint, we recommend that the engineers look at SI simulation, electrical validation, and function validation to make sure that PCIe 6.0 technology is integrated correctly and provides the feature sets that are required for the use cases and for the market is designed for. Most companies can either do these tests internally or come to external companies that offer these services and solutions. Finally, summarizing what I've spoken about, PCIe-SIG has delivered a succession of industry-leading PCI Express specifications that remain ahead of the increasing demand for a high bandwidth, low latency interconnect for compute-intensive systems in a diverse market segments. That includes data centers, artificial intelligence and machine learning, high-performance computing, HPC, and storage applications. PCIe 6.0 specification, the latest PCIe standard, eliminates bottlenecks, allows companies to reach best levels of performance for data-intensive workloads. Thanks again for making the time to listen to us. For more information, please contact me, Vamshi Kandala, or Miki Takahashi. Thanks again. Bye-bye.